So make sure you put your date next to your bell work, on top of your bell work. Today's August 12th. After chapter one's over, you'll have a bell work quiz, and you'll have your notebook out, and I'll say, turn to August 12th and write a definition down. And you just flip to it, and you copy what you have in your notebook. Okay? So it's an easy quiz grade. Because you're doing bell work every day, you just have to keep it organized. Okay? So here's the standard that you're supposed to copy. It's kind of a lot, I know, but this code is actually really meaningful. It looks like gibberish until someone tells you what it is. So the Department of Education, they decide what students should learn, and then they write all of the definitions of things they should learn, and then they tell the textbook companies, and the textbook companies, they do their best to make their books based on what the Department of Education says, and then the department gets to pick the textbooks that do the best job. And then they also tell the schools and the teachers what these standards are. And in my lesson plans, I have to document these standards. And I have to document that you were given a chance to learn them, practice them, and that you were tested on them to see if you mastered them. Okay? So you've seen these your whole life, but I don't know if anyone's ever really explained it to you. So when you see this, the MA, that just stands for math. So if you're writing a standard English class, take a look at what the first two are. It might be like ELA, I don't know. This just means math. 9-12 means this is a high school standard, 9th through 12th grade. F stands for function, and this is just our very first, it's 1.1, it's the very first part of function. Okay, so this code, it looks a little bit ridiculous and meaningless until you actually know, oh, this is just math, high school, what we have to do with functions. Okay, so on my lesson plan, this is what I put today. So I'm going to give you an equation and a graph, and it's going to define a function, and you're going to determine what function it is. We're going to do 4 functions today, and I have a handout for you. These 2 definitions, a function family, a function that shares the same characteristics. So these are all the families. Well, there's a lot more, but here's a lot of the families for algebra 2. So yesterday we talked about linear functions. All linear functions make straight lines. They're in the same family. So their characteristics is that they're straight. All quadratic functions are in the quadratic family, and they all make U's. The parent function is the most basic function in the family. So those are the parent functions. Almost all the most basic ones, they go right through the origin, right through 0, 0. And there's just not a lot going on with them. They're just, there's not a whole lot of numbers in the equation. They're basic. I have some more definitions for you, but you don't have to write them. You've seen most of them in geometry. It's up to you what you write. Don't feel like you have to write this next bit. Look at it and think about it. All right, some vocabulary. So we're going to talk about how functions are different from the parent function. You guys have been using this word reflection for a long time. So you know reflection will make something flip across the x-axis or flip across the y-axis. Thumbs up if you heard the word translation in geometry, right? So you did maybe quadrilaterals or squares or circles. If you translate something horizontally, you move it left to right. You translate it vertically, you move it up and down. You did it with shapes in geometry, you're going to do it with equations in algebra 2. These ones, I'm not so sure. Did you hear stretch and shrink in geometry? So you may have heard dilation. Like, did you dilate circles? Yeah. Or compression even. So if a graph looks skinnier than the parent function, a lot of times it's because it's been stretched vertically. Like, think of a rubber band. If you pull a rubber band up, it's going to make it skinnier. So vertical stretch will make a function skinnier. There's another thing though that makes it skinnier, and that's a horizontal shrink. So it appears the same when you push a rubber band in horizontally and when you pull a rubber band up vertically, it makes it skinnier, right? So there's two ways to describe a skinnier graph: vertical stretch or horizontal shrink. There's two ways to describe a wide graph. Maybe it's been pulled horizontally and made wider, a horizontal stretch. Or maybe it's been like a rubber band that's been pushed down gets wider. So maybe it's a vertical shrink.
Teachers,
Two ways to describe that.
All 12th grade teachers, at this time, please make sure you have taken attention to this period. At the end of this announcement, please release your 12th grade students to the auditorium for our class assembly. Remind your students to bring their backpacks with them. We will release them from the auditorium to go to the next class. Thank you.
Yes, just right underneath those other two definitions. And don't write reflection if you already know it. Don't write translation if you already know it. Write these things if they're new to you. You don't have to write it exactly like I do. You could draw yourself a picture. While you're doing that, I'm going to pass back these handouts for today. These are where you're going to take notes today. Keep your notebook out. You'll still need your notebook in a little while. We're going to do the front of this handout in class. You just pass it this way, and then you pass it that. I always press out like way too many. I don't have to count them. It didn't say that. I'm never counting. You can write on this. This is yours to keep. What you see here is 4 graphs. I was supposed to do one thing before I gave you that. Don't look at your paper yet. One thing I wanted to make sure you remembered before we dove into these notes is how to make a table from an equation. So, a nice linear equation like this. If you were to fill out a table, a lot of times, like in Algebra 1, you would be given x values, right? And what do you do with those x values? Any ideas, guys? How do you fill out your table? Yes, plug them in. Plug them in for x in the equation. You don't need to write that. Don't write the table. Don't write the table. Plug them in for x, simplify, and you get a y out, and then you have ordered pairs. So I just needed to remind you about this before we get into what we're doing. So we would do, take the x out and put that in, and then we would have -9, and then we would have an ordered pair at 2, -9 that we could use to graph, right? Thumbs up if you remember that. So I would do the whole thing. I'd put -1 in, and I would get -7. So I know I'd have another point at -1, -7, right? Okay. Now you can do it with your paper. So at the top, there's 4 blanks. Let me know if I'm moving too So the four function families that we're gonna do here, we're gonna do the constant function, which I think is a waste of time. It's my least favorite. It's totally boring and simple. We're gonna do the linear function, which you guys are already pros at. We're gonna do an absolute value function. What function family is. And then last, we'll do the quadratic. And you did some quadratics in Algebra 1. It's probably memorable because it was at the end of Algebra 1. So really all we're doing is we're kind of recreating these for on your paper. So our first, the constant function, this is the parent function. F of x equals 1, or you guys know that f of x is the same as y. So I'm gonna put that here, but the whole rest of the year I'm gonna put y when I want, I'm gonna put f of x when I want, and they mean the same thing. So this one's actually easier to graph first. We're just gonna go right through 1. My graph looks blurry. So this is 0 and this is 1. This is y equals 1. Up on the y-axis, y equals 1. So all the points on this horizontal line, y is 1, right? So for our table, all 4 of these tables are going to have this same x numbers, just like here, all 4. So when I look at this green line, when x is -2, y is 1. And when x is -1, y is 1. 0, 1. 1, 1, 2, 1. It's going to be like that for infinity. That's why I don't like the constant function. It's just kind of boring. So who remembers what domain means? It's a set of all what true for a function. Domain. What is it? What's the domain? There's some clue on the side over here. What do you think domain could mean? The domains are your x's and ranges are your y's. I did not want to do that. So we're going to put x values here, y values here. Okay, so the truth is, since this green line goes left forever, goes right forever, first off, make sure you have arrows on your graph. I don't want segments anywhere on this paper. You went through geometry, make sure you got arrows. So since it goes left and right forever, the domain is all real numbers. But I'm going to teach you a way to write that with symbols, shorthand it. Instead of all real numbers, I want you to do interval notation. I'm going to do a parenthesis. I'm going to put negative infinity, comma, positive infinity, parenthesis. So this is like the set of numbers all the way through. It starts at negative infinity, goes through positive infinity. That's your domain, left and right forever. Your range is only y equals 1. So I want you to use symbols for that too. We're going to do a bracket, a 1, a comma, another 1, and a bracket. Your y values just start at 1, end at 1. There's nothing interesting about them. It's just 1. This function only moves up and down. So you'll only have vertical translations, just like geometry. In the equation, you might see a negative sign, so you might be able to say there's a reflection, but visually it won't look like it. It'll just look like a vertical slide. So that's our first box, totally filled out. Any questions on the constant function, horizontal line? Our next one is linear. You guys know a lot about linear. If you wanna go ahead of me, feel free. The parent linear function is f of x equals x. Or just y equals x. So the difference between constant and linear is constant just has a number and linear has an x. Now this function has a slope of 1 and a y-intercept of 0. So like I said, same table. And we're filling it into this equation where y and x are the same, y equals x. So here, y would be -2. So we have an ordered pair at -2, -2. Y equals -1 when I plug in for x. So we have an ordered pair at -1, -1. So this is a perfect diagonal. So what we're going to do is we're going to compare other linear functions to this one that goes right through the origin and has just a basic up 1 over 1 slope. We're going to say, oh, well, for instance, this equation would be down 5 because it has a y-intercept down here. So this is the parent. Any linear equation other than this is not called the parent. It's a little bit more complicated. This is the most basic one. So this line, actually the x's go left and right forever. So our domain again is all real numbers, and the y's go left and right forever. It's going to go up forever. It's going to go down forever. So our domain and range are both all real numbers. And let's just say that with symbols to save you from writing too much. This line goes on forever in every direction. So this function can have lots of transformations. It can be reflected. It can be stretched. A stretch looks like a steep line. It can be moved left and right, and it can be moved up and down. What's next, you guys? Anybody? Let's hear it. What's next? Absolute value. Let's do it. Absolute value. Do you guys remember what absolute value does? What do the absolute value bars do? What's the absolute value of -5? +5. It has like a positive effect. What's the definition of absolute value that makes things positive? It's like a keyword. It refers to distance. Absolute value actually means distance. So like -5 is 5 units away from 0 on the number line. And that's why we say it's positive. It's because it's talking about distance. And if we don't go negative distance, we don't have any wormholes yet. Okay, so absolute value is just f of x equals the absolute value of x. So it's the linear function, but with absolute value bars. F of x is the same as y. All right, I'm going to pause, and I'm going to let you guys fill this table out in your group and make a graph. See what your graph looks like compared to the people in your group. Yeah. in the class.
I would think so because it's just I'm just gonna follow me this power. Yeah, it might be like I don't know because it's going backward too.
Pretty much just this.
Perfectly shaped and pointy V graphs. That's your absolute value graph. It should come out as a V. If I said it before you finish it, I'm sorry to give away the surprise. So the absolute value of positive 1 is still positive 1. Absolute value doesn't mean opposite, it means distance, it means positive. So here's the table I'm looking for. And when I graph negative 2, 2, negative 1, 1, 0, 0, 1, 1, 2, 2. I got a nice V shape. So did you try domain and range? Does anybody feel like they know the domain and range? Well, it does go left and right forever. So what's the domain? The infinity and the infinity. Negative infinity, infinity. Not good enough. I've probably written it infinite times. Alright, so let's talk about y values. What is the lowest y value that the v hits? Does it get lower than 0? So we're going to show that with a bracket. A bracket 0. This is like a bottoming out point. It doesn't dip below it. So it goes from 0, but then the arrows go up. So they're going to hit every positive y value. So it goes from 0 to infinity. So this is called the parent absolute value function because it's super basic. There's no numbers. You could put a number here, a number here, but it goes to the origin, and then the slope on each branch is up 1 over 1, up 1 over 1. It's just like the closed and open dots with inequalities. So this means it includes 0. So if our parent function was actually an inequality, like that, which it could be, I would put an open circle here, and then I would have to put a parenthesis. Thanks for asking. Good question. All right, so this function can have all types of transformations. It can be moved up and down, left and right. It can be flipped over. And the slope of the line could change. If I wanted this to be like a steeper V, I could put a 3 in front. And when I draw this graph, I start at 0, 0, and I go up 3 over 1, up 3 over 1. So that's the slope. If I wanted the V to go down, I could put a negative sign in front and it would reflect every number. It would be like -1 times the absolute value of x, so every y would be negative. So that would make the arrows go down. So this can look a lot different. This is like the most basic absolute value. Let's do quadratic. So what is -2 times -12?
4.
A positive 4. Let's get our sign right here. That is a positive 4. Alright. What is -1 times -1? Positive 1. So squaring something also makes it positive. 0 squared is just 0. 1 squared. 2 squared is 4. How many can we write like your u's? Which are really quadratic, not u's. So nice you. Graphic designer in the realm. Digital design? What do you make? Photoshop and digital design? So it's really important that it doesn't look pointy. Like I'm gonna erase mine. Let's try to do it one bit better. No, it's still kind of pointy there, but it's really important that this is a sharp point and this is a curvy U. Let's say we did a bigger table and I asked you to do 3. What's 3 squared? 4 squared is 16. So 5 squared is 25. So as the x value increases, the y value starts to like really get really high. So that's what creates the curve. This is so boring. It's always going to go up 1 over 1 to infinity. Just up a step over a step. Totally lame. But this one, it goes up 1 over 1. And then it goes up 4 over 2. And then it's going to go over 3 up 9 and over 4 up 16. Eventually, it's going to be like 10 and 100. So the rate of change here is always changing, whereas here it's just the constant same step. Constant same steps make straight lines, and changes make curved lines. Same domain rates. So this is going to be a reference sheet for you. We're going to do 3 problems now using it. Like this isn't even really the lesson. This is like the background information. So we're going to do the next 3 problems just in your notebook under your bell work. Keep this reference sheet out. It's not the back. Don't not on the back, guys. I'm going to put the problems up here. So just keep this right in front of you. I'm going to put up some problems for us to actually use this information to answer questions. So here's the name of the section in your textbook, parent functions and transformations. Here's the definition. I made you write down. If you were just taking notes with these slides, this is the information I just had you fill out. This is like really basic. I gave you the details for you to keep. And here's our first question. So this is your challenge. Identify the family that this function belongs to. So name it. And then compare this to the parent function. I'll give you a clue. The parent function goes through 0, 0, right? So the parent function would be here. I'm going to draw the parent function on here in just a minute, but I want you in your groups to try to say, what family is it and how is this different than the parent function of that family? Try to use the vocabulary from geometry. You do not have to write the question. If you want to write the equation, I recommend it, if you can see it.
I think it's the
Are you talking about any groups? Write down answers so I can comment you.
I'm just gonna No, the parent function, she said that it's at the 0. Like that is the 0. Like the line is the 0. I'm writing it. That's the equation.
If you're not using any of the vocabulary, like translation, then you're not completing it.
Yeah, there we go. Okay. Oh shit, it goes up to over 2. I think it goes up to over 2. Oh, up to over 1. Wait, hold on. Because if it's at the 1 there, and then it goes to the 2, yeah, it is up to. They're both there on the right.
All right, this function family is absolute value. How is this one different from the one that we just graphed on your note page? Who can identify a difference? It's up 1. You got it. It's up 1. What's the vocab for up? Or a slide? Yes. Translation. Yep, up 1. So we're going to fancy that up a bit. It's a vertical translation of 1. So I'm going to draw the parent function on here. And I have the parent functions memorized. And the quicker you do, the easier this is going to be. You know, you can't draw on here because you don't have the slide, but here's the one we just did. It starts at 0, 0, and it goes up 1 over 1, up 1 over 1. Okay, so yes, this is translated up 1. Can you see that in the equation? You can. There's a plus 1 here. Okay, so today you're going to be given a picture and asked how it's different, but our goal is to not have a picture, is to just look at the equation and say how the picture is different. Okay, so here you need to be relating this graph to this equation. There's one other transformation. What is it? I heard the group in the back. Natalie, I heard you talking about it a little bit. I heard you guys talking about it here in the front. Jade and Ava. What's the other difference?
What did we say? We kind of talked about the whole thing.
It's
Oh yeah.
It's actually skinnier.
Oh God.
You don't have to write skinnier. I'm just putting it on there. It's been pulled up. It's skinnier than the parent. And I know for certain I can say that it's a vertical stretch of 2. Each y value is twice as high as the parent function. Can you see that 2 in the equation?
Yeah.
Right there. Right there I see a stretch. And I can count the slope. That's what you guys were doing. And maybe you can see it easier than everybody. But it goes from here up to over 1, up to over 1, up to over 1, making both branches steeper. So it's a skinnier. All right, questions? 200. We're doing both of these. Okay, right now in your groups, do this one first. Name it. Talk about how it's different than the parent. Name it. Talk about how it's different than the parent.
Other than looks, and then the other one's quadratic. I don't. Um, 2, and it probably has a.
It translates for the linear one. It translates vertically up to.
So vertical stretch of 10.
Yeah. So.
Vertical translation. Yeah, vertical translation.
Translation.
That's not.
And then quadratic one, it has a horizontal translation of 3. Yeah.
Why 3?
It starts off right.
I'm telling you, every single day I woke up, I just went, man, I gotta clear them.
Yeah, I really just thought about that brushing my teeth this morning.
Yeah, me too. I had to solve, like, how to, the toothpaste on a toothbrush.
Exactly.
Yeah, I had to get the slope on it. Same with Shakespeare.
Taylor was teaching us about spongy.
Oh, yeah. I'm in your class, dog.
So if this equation wasn't here, you could call it 2 things. You could say that it's either a horizontal stretch or it's a vertical shrink. Because both those things do the same thing to a rubber band. A vertical shrink makes it wider and a horizontal stretch makes it wider. Now, this is very specific. You won't get this for a few days. But since the 1/4 is here, the correct way to say it is a vertical shrink. If you called it a horizontal stretch, wonderful. You're in a great place. That's great.
No, linear.
Linear. And then how is it different from the parent? Did anybody see this and think that it was shifted left?
No.
So some people see this and they see the upshift. You can see this as shifted left as well. You could say horizontal translation left too, and that's still right, even with that equation. Okay, what's the second one called? Quadratic. Yeah, how is it different? Okay, we're going to do horizontal translation of 3. I need you to say that that's weird. I need you to see that that's weird. Look at the 3. Now, this parabola has been moved right 3. How is that counterintuitive to what we see in the equation?
Because it has like a square root after it, it's in parentheses, and it's gonna get multiplied by the 1/4.
Yeah, all that. So this minus sign would make me think that it would shift it to the left. I would naturally say, oh, negative is to the left. But actually, horizontal translations are opposite. It's the only thing that's opposite. So there is a minus 3 that actually moves there right. Okay, so that's going to be a little confusing for a while. The horizontal 3, if you didn't have the picture, you might be tempted to say that it's shifted left, but it's actually right. It's opposite of how it looks. This is also wider, right? You already said it. This is also a vertical shrink. If you said a horizontal stretch, wonderful. It's specifically of 1/4. So the parent function goes up 1 over 1. This one goes up 1 over 1/4. The parent function goes over 2 up 4. This one goes 1/4 as high. It goes over 2 up 1. Okay, there's a proportion there. All right, you guys, if you flip over your handout, your homework today is to do the first 6 problems. When I check for it on Monday, it's not going to be like I'm checking right or wrong. I'm checking for effort. I'm checking for vocab. Please make mistakes. It's okay to get your homework wrong. That's how you learn. If you're coming in with 100% right answers to a T, I know you just copied it from somewhere. So please do your own work. It's very easy to see when a math student just copied answers from a text. Do your own work.